Welcome to the fourth installment of the Reliability video series. Now that we have discussed appropriate tool types for the analysis, the next step is to collect data to perform the reliability evaluation. In this module, you will learn to identify types of data that are suitable for a travel time reliability analysis, locate and collect the different data components, and assure the data is of sufficient quality for the analysis. We'll begin our discussion on data collection with the principal data element for reliability analyses, vehicle travel times. The basis for all reliability measures is a wealthy source of travel time data. There are two basic ways in which these travel times can be developed: directly calculated from continuous probe vehicle data and estimated from continuous point-based detector data. The selection of data collection techniques will be based largely on the intended use of the reliability measure, program scope, and available resources. It is possible that more than one of these data collection techniques could be used to obtain travel time data. It is important to remember that travel time and other data collected for reliability analysis should be managed at the disaggregate level. As described in Module 1, averages or samples of data do not provide a complete picture of the range of conditions that occur and can be misleading. Additionally, more robust reliability analyses often require or are enhanced by finer resolutions of data. For instance, when using microsimulation to analyze peak period operations, it may be necessary to collect data in 15-minute or even 5-minute intervals to capture detailed changes in operating conditions. Generally, the granularity of data should match the requirements of the travel time tool selected to conduct the analysis. Traditional travel time data sources that include loop detectors or continuous monitoring sites are certainly suitable for use in reliability evaluation. Increasingly, practitioners are turning to probe data for providing a sample of vehicle speeds. This category includes both GPS-based probe data as well as roadside via Bluetooth or similar technology. More sources are expected to emerge with mobile communications and connected vehicles. Discretion should be used when directly comparing travel times from different methods, as each method may have unique but consistent internal biases. It is recognized that all methods of calculating or estimating travel time data produce some error. Professional judgment should be used to determine whether the likely estimation errors exceed those permissible for the applications of the reliability measures. Agencies should also recognize that near-term and future advances in traffic monitoring are likely to provide more sufficient quantity and quality of travel time data for reliability measures. The travel volumes associated with travel times can be more challenging to obtain depending on which source of travel time data was used. While the traditional sources, such as loop detectors, typically provide volume as well as speed data, probe data is typically just a sample of trips, introducing uncertainty into the number of vehicles on the road. If only a sample of vehicle counts are known, the analyst should do their best to seek additional sources of vehicle count data. Traffic volume is typically measured by vehicle throughput, which can be constrained by congestion or other limiting factors. If traffic demand is desired for the analysis, the analyst should assess the number of vehicles being constrained from reaching the study facility and make appropriate adjustments to volumes to estimate demand. Once traffic volume or demand data that is appropriate for the study type is collected, the analyst can progress with collecting other necessary data. Taking a deeper dive into the data collection process, the components that add to the richness of reliability space are the non-recurring factors. These are the conditions observed to influence travel time reliability by prompting a change in travel demand or capacity. Typical sources of non-recurring factors can include variation in traffic demand, traffic incidents, inclement weather, and work zones. We'll first discuss the idea of variation in traffic demand. To little surprise, the number of travelers trying to use a facility at a given time can vary day by day, hour by hour, minute by minute. This demand variation can stem from something as granular as a shift in a person's daily schedule to something as widespread as general travel patterns across days of the week or months of the year. Referring back to the discussion earlier on travel time and traffic demand data, it is important for the analyst to collect this data over a long enough period of time to capture this fluctuation in demand and the associated impacts on traffic operations. In addition to day-by-day variation in travel demand, there are often times when travel demand and capacity can vary considerably from typical conditions. These spikes in demand can occur due to sporting events, holidays, or other locally significant occurrences that have an impact on traffic operating conditions. Locations, times, and duration of these special events should be obtained, along with their impacts on travel demand and travel time, for the analyst to attain a more comprehensive distribution of travel conditions throughout the travel time analysis period. Along with special events, inclement weather can have significant impacts on traffic demand and facility capacity. Weather history can be obtained through road and weather information systems, National Oceanic and Atmospheric Administration, or similar online databases. Analysts will want to collect dates and times of different weather scenarios, such as clear, rainy, or snowy conditions, and the severity of these events, which can be measured by inches of rain or snow per hour. In very extreme weather events such as severe snowstorm or flood conditions, a roadway may even be closed. Identifying these conditions is also critical to evaluating the reliability performance. Crashes can also be a major cause of unexpected travel time delay. Crash records are typically compiled by state law enforcement agencies and provided to transportation agencies. Crash data should be disaggregated by location, time of day, and severity to the extent or granularity required by the selected traffic analysis tool. It is also of significance to obtain information on lane or shoulder closures, if possible, to understand the operational impacts each crash has on traffic. If this data is not available from law enforcement records, consider supplementing that with logs from a traffic management center or freeway service patrol to provide additional detail. The final primary component that can heavily influence travel times is road construction. Work zones can have significant impacts on traffic operations, considering roadway capacity is often reduced through lane closures, and traffic may be diverted to other nearby facilities. Road work records should be accessible through the department's construction administration. Note that these should also be cross-referenced with incident logs in instances where traffic management activities were undertaken in conjunction with roadwork. Similar to crashes, lane and shoulder closures, along with frequency and duration related to the roadwork activities, should be documented. For data-poor analyses, traffic analysis tools that provide default values or automate entry of data may be able to provide a last resort analysis option. SHRP2 Solutions, developed by the Transportation Research Board in partnership with FHWA and AASHTO, leveraged widely researched travel time reliability data and analysis methods to produce a host of traffic analysis tools. SHRP2 projects LO7 and LO8, in particular, offer built-in functionality to generate a range of data elements for reliability analysis, including weather distributions by city, demand profiles by area type, and incident frequencies by severity. Although referring to default data values can provide analysis options for those with limited access to the necessary data, it can have an adverse effect on the accuracy of results. Thus, it is suggested to locate and apply local data for the analysis whenever possible. Several of the non-recurring conditions require the analyst to identify the corresponding impacts to traffic. For example, inclement weather conditions lower the road's capacity. Similarly, with traffic incidents and work zones, the severity of closures associated with each of those events will have a corresponding effect on vehicle throughput. The impact of non-recurring events can be estimated by collecting field measurements while the conditions of interest are present. Common types of calibration measurements that can be collected to determine operational impacts of the various travel scenarios may include travel time, vehicle speed, vehicle throughput, and queue length. These calibration components of data will prove useful later on in the reliability analysis and will be discussed in subsequent modules. Once the necessary data for the analysis has been collected, the analyst should reassure that all data components have been assessed for quality. This step is vital prior to conducting the traffic reliability analysis, since any flawed data in this stage of the analysis will have a direct impact on the accuracy of the tool results. Data quality is assessed across a range of characteristics, including sample sizes, accuracy of speeds on arterials and ramps, small segment lengths, and limited availability on specific segments. The analyst should verify that the accuracy and completeness of the data is appropriate for the tool selected for the analysis. This module provided an overview of the types of data that are necessary, methods of obtaining the various data components, and the importance of assessing the quality of data for a travel time reliability analysis. In the next module, Module 5, we'll go into detail on what it takes to perform the reliability analysis. Key objectives of Module 5 include preparing data for the model, entering the data into the traffic analysis tools, and performing the verification, calibration, and validation of the model.